Bismillahirrahmanirrahim. Welcome everyone. Today we are going to start the next chapter of the chemistry part 1, that is the chemical equilibrium. Today is its lecture number 1, so we will discuss the introduction of the chemical equilibrium. I have written two reactions in front of you. Now what is the difference between these two reactions? In the first reaction, W reacts with X and it forms Y and Z product. And this reaction takes place only in one direction. So I will say that this one is a unidirectional or irreversible reaction. In this reaction, W reacts with X and it forms Y and Z. But the products are stable and these products do not react again to form the reactants. So this reaction proceeds only in the forward direction. It is a unidirectional or irreversible reaction. The products of this reaction are stable. Now, what is the ultimate fate of the irreversible reaction? Obviously, the ultimate fate is that all the reactants will be converted to products and this reaction finally will stop. On the other hand, there is another reaction in which A reacts with B to form C and D. But C and D are unstable. And under same conditions, then C and D re-react and they again form A and plus B product. So this reaction takes place in two directions. One is the forward direction and other is the backward direction. In forward reaction, A and B are reactants and C and D are products, while in the reverse reaction, C and D are reactants and A and B are the products. So we will say that this one is the bidirectional or reversible reaction. So a reversible reaction is the reaction in which reactants react to form the products and under the same conditions the products re-react to form the reactants. So it takes place in two directions simultaneously. One is the forward direction and the other one is the backward direction. So it is a bidirectional reaction. It means depending upon the direction of the reaction, reactions are of two types: irreversible or unidirectional and reversible or bidirectional. Now, the ultimate fate of this reaction was that all the reactants were converted to products and reaction that stops. Now, what will be the ultimate fate of this reaction? Ultimate goal of this reaction? The ultimate fate of this reaction is the state of equilibrium. So ultimate fate is the state of equilibrium. At the start, when the reaction starts, concentration of A and B is very high. So the collisions between the A and B molecules are at the maximum rate. And therefore the speed of the forward reaction is maximum. But at the start, because C and D, they are not present in the reaction mixer, so the reaction in the reverse direction, that is negligible. But as the reaction proceeds, the concentration of A and B that decreases and C and D that increases. So the collision between A and B, because the concentration of A and B decreases, so their collisions also decrease. it means that the speed of forward reaction with passage of time that decreases. And as the concentration of C and D increases, the molecular collisions of the C and D, they become more frequent, and the speed of the reverse reaction that keeps on increasing with the passage of time. Then a stage comes when you observe that concentration of A, B, C and D in the reaction mixer becomes constant. And now the time passes, but the concentration of A, B, C, and D, they do not change. And when we say that the concentration of A, B, C, and D, they do not change, so has the reaction stopped? Mean after some time the reaction stops? No, that is not the case. Actually, then why the concentration becomes constant? Because the speed of forward reaction becomes equal to the speed of the backward reaction. Now, when the speed of forward reaction becomes equal to the speed of the backward reaction, it means that the rate of conversion of A and B into C and D and the rate of conversion of C and D again into A and B, that becomes equal. And when this conversion becomes equal, then the concentration of the reaction mixer becomes constant. There will be no visible change in the reaction mixer. If the any substance is colored and the reaction mixer is colored, then the color becomes constant. Means the color will not change further on. It will neither fade, it will neither become darker. So the color also becomes constant. At the state where the reaction actually proceeds in both the direction but speed is equal, when the speed of two opposite reactions becomes equal, that is called a state of dynamic equilibrium. So it means chemical equilibrium is not static in nature. Rather, chemical equilibrium is dynamic in nature actually. It is just like suppose that this one is a water tank. Here is an inlet through which water enters in this tank, and here is the outlet through which water leaves the tank. This one is a water tank. Now in water tank, the input of water that is equal to the output of water. So if anyone observes the level of the water in this tank, he will observe that the time keeps on passing, but the level of water in the tank that remains constant. So does it mean that there is no input and output of water in the tank? No. The water is entering the tank as well as the water is leaving the tank, but the rate of entrance and the rate of departure or the rate of leaving, that is equal. So when the rate of entrance of the water and rate of leaving of the water from this tank, they are equal, it means the level of water in the tank will remain constant. So water is not static in the tank. Both processes are going on. Input of the water, output of the water, both are taking place, but at the same speed. So that's why the level is not changing. So here that is not the static equilibrium, that is the dynamic equilibrium. In the same way, in the reversible reaction, it proceeds in both the directions, but the speed of the forward and the backward reaction, they are equal. Now when I say that concentration of all these reactants and products, it becomes constant and it is not further changed, then the reaction mixer at this stage is called as the equilibrium mixer. So the reaction mixer at the state of equilibrium is called as the equilibrium mixer. And when I say that concentration of all these species becomes constant, you know that rate of reaction is equal to change in concentration over change in time. Now what will be the net rate of reaction? Because change of concentration is equal to 0. So net rate of reaction at the state of dynamic equilibrium, that also becomes equal to the 0. The rate of forward and backward reactions are not 0, both are taking place, but the net rate of reaction, that actually becomes equal to the 0. Now, what are the characteristics of the dynamic equilibrium? Can we achieve the dynamic equilibrium in an open container? What's your opinion? So keep in mind that dynamic equilibrium can only be achieved in a closed container. So container should be closed, because when the container will be opened, then some of the reactants and products, if they are in gaseous form, they will definitely escape. Otherwise their vapors will escape, and you will never be able to achieve the dynamic equilibrium, because when some of the reactants and products, they will leave the reaction mixer, then the speed of forward and backward reaction will never become equal, and you will not be able to achieve it. Now next character is that dynamic equilibrium can be achieved from either side. Now what does it mean that dynamic equilibrium can be achieved from either side? It simply means that you can achieve this dynamic equilibrium either by starting the reaction from A and B, or starting the reaction from C and D. So if you start the reaction taking A and B as reactants, or if you start the reaction taking C and D as a reactant, in both cases the equilibrium will be achieved, and in both cases equilibrium concentration of A, B, C and D, they will be equal. Now next, you know that at the state of dynamic equilibrium there is thermal equilibrium as well. This one is rather a condition that at the state of dynamic equilibrium there is thermal equilibrium, which means that the change of enthalpy, that also becomes equal to 0. Because if the forward process will be endothermic, and the heat absorbed in the forward process, that will be plus x kilojoule per mole, then the reverse process will be exothermic. And if that is minus x, then amount of energy absorbed and released, they will be equal, and net energy change, that will be 0. So at that state of dynamic equilibrium there should not be any energy released or absorbed into the system or out of the system. So the energy must not enter the system, energy must not leave the system. Similarly, at the state of dynamic equilibrium there must be mechanical equilibrium as well, and mechanical equilibrium simply means that change in pressure will be 0. Mean if the reactants and products, they involve gases, then the change in their partial pressure at the state of dynamic equilibrium, that will become 0. Mean the time will keep on passing, but there will be no change in the pressure of the reaction mixer. Similarly, that gives free energy delta G, that is also equal to the 0 at the state of the dynamic equilibrium. So gives free energy, that also becomes equal to the 0. Now what is the next characteristic of the state of equilibrium? The next character is that catalyst has no effect on the state of equilibrium. Catalyst will not disturb the state of equilibrium. There will be just a change that uncatalyzed reaction will achieve equilibrium in longer duration of time, but the catalyzed reaction achieves equilibrium in relatively shorter duration of time. So catalyst has no effect, overall effect on the state of the dynamic equilibrium. So similarly, These are some important, you can say, characteristic feature of the dynamic equilibrium. Now, how the dynamic equilibrium can be explained graphically. So let us draw some graphs. Like on x-axis there is time, and on y-axis there is rate of reaction. So when the reaction starts, the rate of forward reaction is maximum, and with the passage of time the rate of forward reaction keeps on decreasing. And when the time is 0 second, at that point the rate of backward reaction is 0. But as the time goes on, the rate of backward reaction keeps on increasing. Then a stage comes when the rate of both these processes becomes equal, and that is the state of dynamic equilibrium. So this shows the rate of forward reaction, and this curve shows the rate of backward reaction. And when both these rates are equal, that is the state of dynamic equilibrium. In the same manner, there is another graph which can be used to show the state of dynamic equilibrium. On x-axis we have time, on y-axis we have concentration. Now, you know that when the time is 0 second, then the reactants are maximum and their concentration decreases with the passage of time. And as the time is 0 second, the concentration of the products, that will be 0, and when the reaction will keep on moving in the forward reaction, concentration of products will keep on increasing. And a time comes when the time passes. A stage comes when the time passes, but there is no change in concentration of reactants or concentration of products, and it purely becomes parallel to the x-axis. Both these curves, they become parallel to the x-axis, and we say that dynamic equilibrium is achieved. So this rising curve is for products, and this falling curve is for reactants. And these curves show that at the state of dynamic equilibrium, the concentration of products is greater than concentration of reactants. But keep in mind, this is not always true. Mean you cannot say that always at the state of dynamic equilibrium the concentration of products will be greater and reactant will be lesser. Rather, the case may be something like this. Like this one. Mean when these both curves, they become parallel to the time axis, this shows that dynamic equilibrium is achieved. Now this one is the curve for the reactants, and this one is the curve for the products. And these curves show that at the state of dynamic equilibrium, the concentration of reactants is greater than the products, because this one is the dynamic equilibrium when both these curves, they become parallel to the time axis. So in this case, concentration of reactants is greater than that of the product. And what can be the last case? The last case can be, here is time, and on y-axis there is concentration, and equilibrium is achieved something like this. The falling curve is for concentration of reactants, and the rising curve is for concentration of products. So in this case, at the state of dynamic equilibrium, the concentration of reactants and products, they are equal. It means that at the state of dynamic equilibrium, reactants may be greater than products may be greater than reactants, and reactants and products, they both they might be equal to each other. So all these three cases may be at the state of dynamic equilibrium. Reactants are equal to products, true. Products are greater than reactants, true. Products are lesser than reactants, true. So any of these three, any one of these three, that can happen at the dynamic equilibrium. But what will always take place at the dynamic equilibrium, what will be always true at the state of dynamic equilibrium, that is the point which says that concentration of the reaction mixture does not change with time. There will be no visible change in the reaction mixture. There will be no macroscopic change in the reaction mixture. So concentration of all the reactants and products, they will become constant and they will not change with the time. But they may be equal, they may be lesser, greater, any case that can be at the state of dynamic equilibrium. So this was the concept of the dynamic equilibrium and some graphical explanations. Next time we will come up with the topic law of mass action and the equilibrium constant. Till then, Allah Hafiz.